Much. How are we all doing? Everyone good? High energy from the break? Yeah, I can see. A question for you before I start. How many of you have played the game Half-Life before?
Only the third one.
Oh yeah. Quite a few. So, could you keep your hands up for me if you have Half-Life installed on one of your devices somewhere? Okay. So we've all come prepared for the talk then. Not your devices anymore, sorry. Of course, joking. But, so my name's Ryan Saridar, as was mentioned. I'm a cybersecurity consultant with JumpSec, and vulnerability research is very much a hobby for me. So my hope with this talk is basically to give you guys a little bit of insight onto the journey that I took in going through and finding and exploiting this vulnerability, but also hopefully to give those of you who don't have as much of a background in vulnerability research and memory corruption vulnerabilities a little bit of an understanding. To do that, I'm just going to build up a little bit of background first and some basic theory. So quickly, just on the point of memory, within a process memory space, as you can see, there's quite a lot going on. But there are three things that are important for this. First of all, being the program code, which is just shown in the image there, if you can see it clear enough, as program image. And when I say code in this context, I'm not talking C or C++ or any high-level language. It's all machine code that's embedded in the executable that's used and can be loaded and executed by the CPU immediately. And the same goes for any of the library code that's loaded. And the stack, if you're not familiar with it, is just a basic data structure that's used to store program information for some specific purposes. But I do want to go in a little bit more on that just to see where the vulnerability part comes in. So this is just a picture of a stack and how it might be used by an operating system. And particularly one thing that you'll notice there is the stack grows downwards. So it's a stack just in the sense of a physical stack that you might know when you stack up your plates. The concept is basically that you put a plate on the top, the next plate you remove isn't going to be from the middle or the bottom, you have to take it off the top as well. And with the stack here, it's the exact same thing. And if you think about a function in code, then starting from the top there, if you're running an existing function and you're going to call another function, then that function might have certain parameters. And so the function will put those parameters onto the stack before it gets into the next function. Now, that's valuable because that function can then refer back to them and grab those values. But before it transitions over and moves into the next function, you've also got this return address value, which is really important to know about. And the return address basically is the code leaving its mark of where it started. So if you're sitting in a function and you've called, function A calls function B, then once function B is done running, you want to return back to function A. And so this return address is the location in memory where the instructions are for that function A, where you left. And then this, in a different color, is called the stack frame for function B. And that's basically its own context of the stuff that it's putting on the stack, including stuff like local variables. Now, what's important about this is if you think about your local variables, maybe within my function B, I'm going to have some input. And I'm going to allow users to type their own data in, and when they press enter, it's all going to be copied into this variable. But if I have, let's say, a 10-byte variable assigned there, and I take in input without safely checking that the input is of the right size to fit in that box, then it can overflow. And that's where you have your stack-based buffer overflow occur. And what can happen if you go sufficiently large in the overflow is you can actually overwrite this return address. What that means is when this function is done running, it's going to look to that value that you put in there as to where it's going to go back. That means that we can leverage this to control program execution. So to start with, my inspiration around exploring the vulnerability that I have is actually from a few years ago. And my journey developing this and finding the vulnerability starts about 2.5 years ago. This is something that popped up 3 years ago. Somebody had found a vulnerability in Half-Life, another buffer overflow based one, particularly one that targeted a specific command line parameter, the dash game parameter for the game. And if you provided too much data to that parameter, then the overflow would occur. And so based off of this, I was very interested to pursue that concept, and I thought, well, if that dash game parameter might have that vulnerability, then perhaps other parameters that the game supports might too. And so I went into a bit of exploration around that. Now, you can see here a page from Valve, their official page, which has Gold Source is the game engine that was used to implement Half-Life. It has a bunch of command line parameters here that are possible, and there's many more below that, but the screenshot's not big enough. So my initial idea was, alright, well, it's just going to be dead easy. Let me grab the whole list of command line parameters that are there. I'm going to put them all together in one big string. I'm going to write a script that will take 1,000 characters, let's say the letter A, and put them after each of those parameters. I'll throw that at Half-Life, and if it crashes, then I know probably something's there. And I did, and it did. And so from there, I went through a little bit of a process of trying to identify, all right, which parameter is it that I found? And I did a binary search type approach. I split the payload in half. So let's try the first half. It crashed. Great. Let's try the second half. It crashed. So I thought, well, I've got 2 vulnerabilities on my hands. That's excellent. And so I continued the binary search approach. Let's see. Let's identify which ones are they. And I halved each of them. Nothing. I halved the next ones. Nothing. And I wasn't splitting the 1,000 characters in half. I was just separating out what parameters I was actually testing the vulnerabilities for. So after a little bit of thinking and checking, I realized that the overflow wasn't occurring on any of them. It was occurring on the input as a whole. And so that's where basically I go into my exploration of this vulnerability. Now, this is where I need all of your help. I need a little bit of luck wished upon me, because I had the brilliant idea for my presentation that I'm going to show and not tell, which means demo. And that's what it will be for the rest of this.
Fetch the goat.
Yep. So, I'm going to break out of this. I'm going to actually show you so that you guys can find the vulnerability with me, and maybe we can see some sort of exploit for it. So, to start with then, I've got Half-Life ready. And just sort of like the magician showing you his empty hat, I'm just going to show you I have no command line parameters set. If I click play here, Half-Life will launch. Shall we load a game?
Speedrun it.
Yeah. Cool. So I'm actually going to show you that initial buffer overflow that I was talking about. Too much data just being passed into the program, and you get a crash. And I wrote a quick script, and I can show you this script. It's not particularly complicated, just for your interest. It's just going to take 5,000 characters and copy them to my clipboard. That I can then use here. The frustrated screaming of a vulnerability researcher. And then if I click play, you'll see nothing pops up at all, and then it just stops. And that's because it's crashing before it even gets to rendering anything. So in order to dig into this and tear it apart a little bit, what I'm going to do is I'm going to use a debugger and figure out what's going on. So to start with, I'm going to use this thing called WinDebug. And I'm going to launch Half-Life, as you can see from my previous testing. And I'll paste in those A's that we put in. If I go into a debugger session here, you'll just see this LDRP do debugger break. It's just breaking for me right at the start before I actually start execution of the game, just to make my life easier. It allows me to enter any breakpoints I want or anything. And I'm just going to go ahead. And so, if you have a look at what we've got here, you can see access violation. And so it seems promising on first sight, but when I saw this initially, I was actually concerned, because what you'll see here in the instruction is a move instruction that's it's crashing on. Now, when I was explaining to you how the stack-based buffer overflow might work, the concept is that you're putting in so much data, you overflow that return address, and so when the function returns, you're going to run into an issue. And particularly, I would understand if this was the function returning, but that's a move instruction, not a return instruction. So I want to understand what's actually going on there and see if there's anything more to this. To do that, I'm going to pull up a piece of software that's already open called Ghidra. And Ghidra is just a reverse engineering tool. But if I go over here and look at the crash, you can see on the left there, that shall highlight, this address, 140.1153. And I can take that and put that into Ghidra and ask it to tell me, quite a few of them, ask it to tell me what's at that location. And we can see the instruction that we found in the debugger as well now, and everything else that's around it. I could do this with the debugger as well, but it's just nice and clear for you to see here. And you can see that on the right-hand side, it's tried to decompile it, and it's just giving you its interpretation of what the C code version would look like, obviously imperfectly, because it's not able to reverse it fully. But we can get a little bit of insight as to what's happening here. And if you have a look at this function, we can see that ret instruction that I've just highlighted is not too far at all from the move instruction that we're stuck at. So, if we can pass this, then potentially we can hit that ret. Let's understand then what's actually going on here. Now, if we look at this move instruction, we're moving something from the EAX, which is a register in the processor, into this EBX plus 4 location. And those square brackets basically mean that it's doing the math on EBX plus 4, and then it's treating that value as an address. So whatever EBX plus 4 is should point somewhere that it can move data to. And if we have a look at EBX, we can see here what its value is. 41, 41, 41, 41. To some of you, you might know what that is already, but to those who aren't familiar, that's the hex character for uppercase A, which I absolutely blasted at the program. So what we're seeing is that the EBX value has actually been overwritten by my payload. So, clearly, when the program runs usually without me interfering, there is some legitimate value in there that it can move something to. So in order to determine what that is, I'm going to run it again without my overflow, without my spam of characters. And what I'll do is I'll put a breakpoint the next time it runs at this address that I've got, so I can actually see if, without any additional data from me, what that value would naturally be on its own. So now I'll put a breakpoint there. When I hit go, you can see we're on that instruction this time, no access violation, and we've got ourselves a value here. So whatever that is, plus the 4, that's going to be a memory location that it can write data to. So I can actually take this, incorporate it in my payload, and then at the exact location where the data is that's overriding that EBX value, I can place that, and then it should work. Skip the step. Now, for the sake of time, I'm not going to go through all of that, and I'm just going to cheat a little bit and go back to my original case. Let me just actually copy this value. So if I copy the overflow payload, then when I go, we find ourselves at this location again, and I can set that EBX register manually to here. But realistically, in the process of developing the exploit, you'd incorporate that in the data that you're sending over. And something you can do to identify where in that string of long A's this actually corresponds to is there are pattern generating scripts that generate unique patterns, and then based on the value that you identify in the EBX register, you can then find the offset and incorporate this address value there. So now that I've set that and I click R just to check the registers again, you can see that that's now correctly at the right position. And if I step over, we can see here, go. Cool. So we can see here, access violation, except this time the instruction that it's trying to execute is that 41414141. And that is because that's the value of our EIP register. That's the instruction pointer register that tells the CPU where the next instruction that it needs to execute is located. So that means that the return successfully grabbed that value off the stack and put it in the EIP. Awesome. So from here, where do we go? Well, now we have the ability to determine what's in the EIP register. We can tell it to execute any section of memory that we like. So how do we actually leverage this? Well, we could point it to some code within the application that we know is already bad, but they haven't, unfortunately, included any malicious code inside the Half-Life executable. But we can leverage our ability to provide input to the program. And if we look, we've got the stack pointer that's going to point to our data that we put in. So you can see there all the A's. That means, ultimately, that if I can find something that can jump to that stack location, then I can essentially include shellcode in the payload that I send as part of the command line arguments, and it will jump straight to it. Now, a couple ways of doing that. First of all, I can do a search on the entire memory space, and just to show you something, I'll type lm, which is list modules, and you can see here all of the different modules that are loaded in the application and their address ranges. So this is what I was referring to around the program code, and these are all the libraries, the library code that I was mentioning, effectively. So if I go and do a search, I'm going to search memory, starting at 0, length, till the end. I'm going to look for this jump ESP instruction, jump to the stack pointer. And just to show you what that looks like, I'm going to use this online assembler. I'm going to give it the jump ESP instruction, and you're going to see that it corresponds to the bytes FFE4. So I'll put FFE4 there. We can see a whole bunch of different options to do that. So that's great. It's easy and straightforward. Now the hard part of this exploit. And now I'm going to introduce you to something called ASLR. We're talking about mitigations against these kind of attacks now. ASLR stands for Address Space Layout Randomization. And if I go back to that list of modules that you saw here, effectively, if ASLR is enabled, then certain compatible modules will randomize the location that they start at each time, which means those instructions that I just found the addresses of, I can't rely on them consistently, because if I use it now and I restart my computer, it's going to be a different address for the same instruction. So how do I get around this? Well, there are a couple of ways that people usually do it, but I'm going to show you. If I open up another program called Immunity Debugger and have a look at Half-Life, I'm going to use a tool here called Mona, which is going to actually check which of the modules that are included have ASLR enabled. And you can maybe hardly make it out, but the top one that I've got highlighted there is hl.exe. That's the Half-Life executable. The rest of them all have it enabled. That's no surprise, really, because these are all modern Windows binaries, whereas Half-Life.exe, 98, I think the game came out. So, yeah, they haven't done much for that. But it also means that if I can find that jump ESP instruction within that memory space, then I have my ticket. And I have an exploit that can reliably work time and time again. Now, if I look here, and I put in my search command, the starting address, right up here, for the Half-Life module, then I'll just set the length accordingly. Nothing. So there is no such instruction within that space, and that complicates things a little bit. because I need to find some equivalent way of using that memory space to trigger that jump to ESP style behavior. And this basically is where things get a little bit more complicated. I did a bunch of additional searching. I used techniques like checking for effectively spaces between certain instructions and return instructions. That's effectively forming, if you're familiar with the term, a rock chain. And I developed this to get around this problem. Unfortunately, I won't be covering it here. And that gets me on to the next point around this vulnerability, which is this is unpatched. I found it about 2.5 years ago, initially. I reported it to Valve. They did nothing. I reported it again to Valve. They did nothing. And then a couple of years later, I found an evolution to the exploit, and still nothing is done. So about 2.5 years after it's found. And the last time that I was able to see from the Steam database that Half-Life was updated was 3 years ago. So they've abandoned this ship. And that's why I'm not going to go into all the details around crafting that rock chain and how that works. But I won't leave you hanging. I'm going to show you it functioning. So I've got the script here. So Mona has functionality to do that. It wouldn't find something that advanced. It was a lot of manual effort to get the rock chain together because it uses a lot of unconventional techniques to get things working. I did try Mona first, but unfortunately no dice. So one thing with the command line argument point is that it's an overflow of the entire command line argument string, which also includes the part of the executable. So what your payload actually looks like is going to depend on what that is. And so I'm using the default. I'm just going to accept that. And also a point here is that if you launch the game through Steam, it appends automatically a -Steam parameter. So we have to account for that, because if I don't subtract the additional length of the payload that's required to accommodate for that parameter, then it's not going to work. So I'm going to say yes to launch via Steam. And now I've got something copied to my clipboard. I'm going to stop the debugging session here. And this one. We're going to go back to Steam. We get a calculator. So you know, like the magician with his hat. I showed you it was empty. So, just going back in the timeline a little bit to when I first found this about 2.5 years ago, as I said, I initially submitted this as a bug bounty. At the time, it wasn't accepted because this was all it was, and whilst there was a vulnerability, there wasn't an easy way of executing it for a typical person. You'd have to social engineer someone into putting all of that command line data in themselves. So since then, I've done a lot of exploration around this, or a bit of exploration. Every once in a while, I go back and pick it up and think, is there something more I could do here? And I found a way of leveraging it that uses local privilege escalation. And the way that works, which I'll show you quickly, is if you go into the Steam folder, not Half-Life, sorry. We want the user data folder, and then I can go to this is an ID that represents a particular Steam account that's logged on in the system. If I go to the config here, you can see this local config.pdf. Now, when you log in on Steam with a user account, there's no natural link between the user account you've logged in with versus the user account that you're using on that Windows system, because you could theoretically log in from any of them. As such, this local config file is available for any user on the system to modify. And what that means is, since it stores the command line parameters, and you can see here, there's my payload, I could go and edit this if I was another user on the system, and then the next time you run Half-Life, there's my callback. So this is the way you can leverage it for local code execution. I did resubmit this with them, and at the time I was told they couldn't accept it because somebody else had already found this vulnerability before. So I said to them, "Was that me?" They said, "No, someone has found remote code execution with this. So be wary." I do have a couple of ideas around how that might have gone about. A couple of things I explored, but where there's potential room to do more. I'm not going to go into it here, but if you're interested, you can catch me off the recording. I'm happy to discuss it. Cool. Now, just a point on mitigation before I wrap up with this. What can you do about this? Well, they haven't patched it. They have no intention of patching it. So the number one thing you can do is uninstall it. Now that's no fun. So what you can do, and I haven't tested this and seen if there's any impact with Steam in other capacities, but if you go to that local config file, then you can actually edit the permissions on there and restrict it to a particular user account if you know that user is the only one that's going to be using it. That will cover the local code execution piece. As for anything else that may arise out of this, I think uninstalling is the only option. All right. Thank you, guys. Any questions? Yeah.
Try similar blue shift.
I haven't tried those ones actually. I can if you want. Oh no, I can't actually. They're not installed. I don't know. I don't think we have the bandwidth for that. I did try other games though. So there's a piece of this. Unfortunately with the time limitation, I can't show everything that I went through. But I did go and actually do a little bit of more reverse engineering on the Ghidra side. And if you have a look at this function, you'll see here there's a string that's included in it. And using that, basically, I managed to find from source information online the particular function that's vulnerable and what was going on under the hood. And I noticed that was present and that function would still be present in modern games. So I did try, I tried Portal. I tried Team Fortress 2, all the modern Source Engine games, and they have actually patched it on those ones. They just neglected it on this one. So, great. Yes?
Out of 17.8 hours of playtime, how much of that?
Well, in reality, when I do debugging, unfortunately, it will just suspend the process entirely. So I wonder if it's accumulating at all. However, how much of that time was calculator? Possibly half. Yes.
Have you considered looking at some of the more modern source games now that a lot of their source code?
I may have, allegedly. Yeah, so I've done a lot of exploration on stuff like that, going through Source SDK and so on. No comment about any leaks. And just doing some searches for like memory corruption possibilities and so on. There are some insecure input handling functions that are used in places, usually ones that are out of scope because they're odd tools here and there that might not have the highest impact. They have also made a lot more of the functions memory safe, and they've included wrappers in that code just for safe memory handling. So I've explored it a little bit, and I'm sure there's much more to explore, but I've had no luck there yet. Anyone else? Oh, yep.
Unrelated, but I'm surprised to be running halfway.
I'm not good enough, unfortunately. I stick to my talents. Awesome. Thank you, guys.